better.
Okay. So once again, I'll just rewrite it.
I was going to rewrite it.
Really?
Yeah.
Okay.
Yeah, pretty fun. Yes. It's a great example of something we can edit.
It's called hyperbolic. If all of the eigenvalues of the derivative matrix at that point have non-zero zero. Is that better? Can you see it now? Yeah, I also couldn't see it from this angle either. So there it disappeared. Okay. Fine. So then I talked about the Hartman-Gilbert theorem. I introduced what it was, but let me now formalize it. So theorem. So I have a tendency to talk about history of math a little bit, and Hartman and Gilbert's theorem I think came around in the many years ago, but within our century. But the person that really kind of figured out that you can classify the behavior of differential equations by looking at the eigenvalues was Henri Poincaré, and I think the fact that he saw a system of differential equations and just said, yeah, look at the eigenvalues. I think that's remarkable. I cannot get over that. That's very insane. But we could not understand anything about dynamical systems without that. I think he actually did his PhD dissertation on the nature of equilibrium points and things like this. So I mean, the idea that you could look at something like that and just figure that out, I think is utterly remarkable. It's the same idea that when they showed Gauss this integral minus infinity to infinity, he just said, yeah, that's too powerful. He said, don't waste my time. So I don't know how they do this. Okay, I just want to bring that down. Okay, so the Hartman-Gilbert theorem says the following. So once again, consider a dynamical system, x prime is equal to fx, where once again I will assume that f is of C1, so it has continuous first order partial derivatives. If, and I should say, just to be precise, the flow here associated to this I will always denote by phi t. So if A is an equilibrium point of the system that is hyperbolic, I should say. So A is a hyperbolic, then there exists a neighborhood, I'll call it N, of this point A, where the flow is topologically equivalent to the flow of the linearization of the dynamical system at A. In other words, there is a homeomorphism between the nonlinear dynamical system and the linearized system in the neighborhood of the equilibrium. So that's the Hartman-Gilbert theorem. In other words, in the neighborhood N of my equilibrium point A, the orbits deforming. So for lack of a better word, it can be deformed in a continuous sense into the orbit of the linearization. In other words, the orbits are the same. Yes?
Is this what you meant before when you said that you can take a nonlinear system and make it into, or like approximate it into linear?
Yes.
The theorem that says all
Yes.
that?
So the idea is that we don't know how to do things with nonlinear systems, and the only way we know how to study nonlinear systems is by linearizing them in the neighborhood of some equilibrium. So in other words, this is the whole tangent space to my manifold idea. That I don't want to deal with the manifold, I want to deal with a neighborhood of a point in the manifold by introducing a tangent space. So it's the same idea. So in other words, they are the same. And the proof of Hartman-Grogan, I will save for you for a graduate level differential equations course. It spans many lectures. I don't want to get into it. Ironically, no, it's on camera. I have to watch what I say. I will not say it. You can ask me about the graduate level course afterwards. I will not say it until again. Yes, okay. To watch what I say now, which is a very difficult thing for me to do.
You could edit it.
Sorry?
You could edit it.
But then I forget when I said what I said. That's a big, then I have to watch it, and I don't like to watch it. No, that's too complicated. I need people to do that for me. I don't have so much to do. Okay. Okay. So definition. So in other words, Hartman-Grogan allows us to study nonlinear systems completely in terms of the equilibrium point. So the equilibrium points characterize everything we need to know about these nonlinear differential equations. Okay, and related to that is this definition. So this is the key definition. In some sense, you already know this definition, but I'm going to write it out anyway. So an equilibrium point which I will call once again A of x prime of x, is called a local sink. So there's that word again. Whenever the eigenvalues of the Jacobian matrix at that equilibrium satisfied. So the real part, RE, of the eigenvalues, which I will denote by lambda, which is the common notation, are less than 0. So if you compute your Jacobian matrix and the eigenvalues at that equilibrium point are negative, or the real part is negative, that point is a local sink. If you compute it and they're greater than 0, it's called a local source. Or just source. There's no such distinction between a local source and a source. If it's locally a source, it's always going to be a source. Yes?
Remember how you said any solution to a system is e to the thing?
For a linear system.
Oh, not for...
No. We cannot rely on that.
But it doesn't have to do with why that's true.
No, not at all. So this comes straight from Poincaré's results. And in some sense, I didn't even have to do the linear systems thing. I could have just started here, but I wanted to give you some motivation for why the nonlinear case is much harder. So that only applies to when you're solving linear systems with equations. We can't solve these internally, so we can only tell you characteristics.
Sorry.
No, he's not.
So, at each equilibrium point, you got a description of what's going on locally.
Yes.
So, you're kind of saying it doesn't matter what goes on elsewhere?
For the local behavior. We also have a theorem that will tell us globally what's going on as well. but we have to understand, so there's 2 points to this. When you're studying a nonlinear system of differential equations, you want to tell me about the local behavior, which depends on the equilibrium points, but then also the global behavior as well. The global stuff is much harder. It's much harder. We only have a very limited set of tools that will allow us to tell us something about the global behavior of the system. But locally, it's just computing eigenvalues and things like that. So we can always say a lot about local. But that's a very good question. So if it doesn't fall in one question, sorry.
Could you remind us how do you define local again?
Within the neighborhood of my point. So if this is my equilibrium point here, so where's my knife? So let's say this is x1, x2, x3, x4. Locally, I mean just the orbits of the solution within the neighborhood of this point.
What determines the neighborhood?
That is an abstract idea. It just means within the vicinity of the point. It's a general idea. There's no specific number you attach to it. It's as big as you want it to be, as long as it does not intersect with the neighborhood of another point. But you see, it's much easier than this. This is getting too abstract. When we do examples, it's much easier. So, if all of the eigenvalues are negative, that point is a sink. If all the eigenvalues are positive, it's a source. But what if you have a mix, like on your midterm? What if one of the eigenvalues is positive, one is negative, then what happens? Then it's a saddle. Yes, because the linear case is a special case. So the eigenvalue description has to be the same, but the solutions are wrong. Okay, and a hyperbolic equilibrium point that is neither a source or a sink, as you know, is called a saddle. Okay.
So the other possibilities don't arise in this case?
The case of the zero eigenvalue,
Yeah.
it comes up, and I'm going to do it. Yes. But I'm saving it for right now. Okay. Give me a second. Okay, so that covers how you describe the behavior of solutions near an equilibrium point. You just look at the eigenvalues in the equilibrium. We have to talk about, so I might as well just write it out instead of just speak. So now I want to talk about, very quickly. So for linear systems, we have the stable space, the unstable subspace, and the center subspace. That was very nice because in linear systems we know the eigenvectors and stuff, and we have a linear space we're looking at. In the nonlinear systems case, we don't have such a nice linear vector space because our space in general is ordered. So we have to generalize that now to not subspaces, but manifold. So instead of the stable space, center subspace, unstable subspace, now we have the stable, unstable, and center manifold. So it's a generalization of the linear subspace case from before. So, in other words, if A is an equilibrium point of the dynamical system, it is useful to know which orbits or solutions are attracted to A as t goes to plus infinity, it is also useful to know which orbits or repel. So just like in the linear case, but now we're being much more general. Okay. So we generalize the idea of the, so as I said before, the stable, unstable, and centered subspaces defined previously as follows. Okay. Namely, we call W, so this is the standard notation. So instead of ES, now we have WS. And we call WS the stable manifold. And this is, so we don't need to get into manifold theory, it's just what they're called. But this is a differentiable manifold. So you know what that means now, hopefully. A differential manifold of an equilibrium point A that is tangent to ES. So now you have your vector space that's corresponding to the span of the eigenvectors associated with this eigenvalue. But the stable manifold is tangent to that vector space. So it's more general. So that's where the orbits live, tangent to that space. So to every stable subspace, you have tangent to a stable manifold. And that's where the curves and all the solutions live. Yes?
Yeah, for the linear one, there was for a stable subspace you had eigenvalues.
Yes.
Is there something like that for this?
Yeah, so you have the stable subspace that has your eigenvectors in it, that's the span. And tangent to that is the stable manifold. So this is where the solutions live. When you see curves, when you draw solutions to differential equations, they are living in the stable manifold or unstable manifold. So it's more general than that. So that machinery is still there, but this is not on top. Because we still need a vector space. This is more general. So you have the stable manifold. And similar, so all orbits in WS, we say are asymptotic to A as t goes to infinity. Similarly, we have the unstable manifold, which I will call WU, and you can imagine it's just a differentiable manifold that is tangent to the unstable subspace EU at my equilibrium point. So at some equilibrium point, you have the unstable or stable subspace that is spanned by the eigenvectors associated with the eigenvalue, and then on top of that, tangent to that, you have the corresponding manifold. And that's where the solutions live. That's WU, so this is your unstable manifold. And then, of course, the remaining case is the very important WC, which we call the center. And this is the same thing, it's just tangent to EC, which is the center subspace. Now, I have to, this will answer the question now about what do you do when there's a zero eigenvalue. That is the case that I have been avoiding since the beginning of time, because I'm saving enough for this. it's not in general problematic if you have a zero eigenvalue. But if you have more than one zero eigenvalue, then it's a problem. So let's see what I mean by that. Because if you compute your Jacobian and you get a bunch of zeros, what do you do? None of what I said fits in. So it actually leads to a bunch of complications. But luckily in this course I will not give you too many of these complications. Because it's not even hyperbolic then at that point. So what do you do? So WC, which is the center manifold, contains orbits or solution whose asymptotic behavior is not determined by linearization. So that's the point here. If you have a zero eigenvalue, it means that the linear approximation you took was not good enough. And that is a problem because if you take a higher order expansion, it necessarily won't solve the problem either. So there's no good way to deal with the center manifold case or a zero eigenvalue case. There are special cases, which we will see some, that allow you to say something about the system. But in general, it's a very difficult thing to do. So I will talk about this later in our examples, actually. But there are some methods that can help here, but there's no general way to deal with it. And one of the methods is actually called centered manifold reduction. But that's too complicated for this course, so I will try to avoid this case. But in general, it will not be the case that you have every system you study as a zero eigenvalue. Most of them will fall into a single source of saddle. So let's go. Okay, so that is just the more general way of how we generalize these subspaces. And the key point is the following. And the key point is that the dimension of WC, WU, and WS is the same as the dimension of EC, EU, and E. So the dimension of the manifold is the same as the dimension of the corresponding subspace. Okay. And that leads us to the following theorem. So this theorem, which is called the invariant manifold theorem. It says the following. So let x equals to a be, once again, an equilibrium point of x prime is equal to f of x. And let ES, EU, and EC denote the center, stable, all that stuff. The stable, unstable, and center subspaces of the linearization at A. the linearization at A. Then there exists a stable manifold. So I'm just formalizing what I wrote. Then there exists a stable manifold tangent to ES at A. There exists an unstable manifold tangent to EU at A, and a center manifold tangent to B center. And this is the technical point that I wanted to just formally state for the case of the zero eigenvalue. So maybe just a technical point, or note maybe. Ws and Wu are uniquely determined but there can be an infinite number of center manifolds. It's a very difficult case to handle. So there's a lot of people who just study center manifolds, and it's much related to the idea of bifurcations as well. So we can talk about this later, but it's too advanced for a second year undergraduate course. I can talk about it if you want, but I mean, I want to do computations and examples as well. So. Oh. What else do I want to say? Any questions about it? Okay. Is most of the class still with me? Okay. It's not that bad, it's just definitions. What you have to do is you have to visualize these things. Alright, we're almost there. So now, I will talk about the question of global behavior. So as I said, go back to my diagram here. So call these equilibrium points, which I'm completely making up, by the way. So let's say locally you have orbits that do this, or do that, or something like this. Which one of these points, if any, will the system settle on after an infinite amount of time? Is there one state in particular, in terms of its global behavior? That's what I mean by global. So locally, it just means within the vicinity of some point, what are the orbits doing? Globally, I want to know what does the whole system look like after a certain amount. So that's the question now that I will attempt to answer, but it's a much more difficult question. So, global. And I just want to put a warning here. So maybe on your final exam, I will just ask you to describe global behavior of a bunch of dynamical systems and make you cry for 3 hours. It's very hard. On my PhD exam, there's 2 ways to do a PhD. One, you can hang around your supervisor for 6 years and just like do what you're told, which I'm not going to do. So, or you can find things and publish them and do these things. So that's a quick way. So I did that in the latter case. And every time I submit a paper to the journal, the referee comments come back, they're anonymous. They say, the analysis was nice, but you must give an analysis of the global behavior of the system. And I cried for like 2 years. It's very hard to do. And I knew that they were going to come back and ask that question, but I tried my luck. It never worked. So it's very hard, actually. But don't be discouraged. You can do it. So the simplest type of, actually no, I don't. I would be more precise. So let me start off with the definition. And this may be something you've seen in your calculus courses before. I hope actually. Okay, so let phi p be the flow of the system. Okay. And let A just be some point. So not necessarily an equilibrium point, let's just say it's some point in your space. We say that a point, let's call it x, in Rn is in omega, that's in omega, limit point of A if there exists a sequence say Tn to infinity, such that the limit as n goes to infinity of phi Tn is equal to x. So we say, therefore, that x is an omega limit point of A if there exists a sequence such that when you take its flow, the limit, you get that point back. In other words, all of the orbits are attracted to that point as t goes to infinity. That's why I put the flow here. So did you guys learn about limit sets in calculus? Yes, you had to. Yes, no, maybe?
I did.
You did? Okay. So this is the same idea. We're using that concept from your first year practice. But you will see it if you take a course in topology for sure. If they still offer that. No problem. Oh, well, that's pretty useless. Yeah, I know. And the set of all such omega limit points is called, as you can imagine, the omega limit set, which we denote omega by. And similarly, we call the alpha limit set when t goes in the opposite direction. So for t going to minus infinity, so backwards, we call alpha of A the alpha limit. Alpha and omega. Start from alpha. Yes.
Similarly
For the sequence Tn going to minus infinity. Minus infinity. Okay, but that's just a topology or calculus definition. How does that apply to what we are doing? It applies as follows. So theorem. Let phi t be the flow of x prime is equal to f of x. Then, for all A, omega A is a closed, bounded, and invariant set. So, finding omega and alpha limit sets also is another way of finding invariant sets of this. Yes. So that's how we relate So definition. This will finally answer the question of global behavior. Now I will tie all this together. Definition. We call the future attractor I'll call it capital A, plus, so it attracts. I don't know how else to describe plus. I don't want to write future attractor, so I'll just call it A plus. Hopefully you will get such a mark on these. Is the smallest closed invariant set such that the omega limit set belongs to this attractor. In other words, finding the omega limit set tell you what the future attractor is going to be of your system, and that tells you what the global behavior of your system is. It's all related to finding these annoying omega and alpha limit sets. And how do you do that? I have no idea. Yes.
Did you say that it was a subset of A plus?
Yes, that seems should say subset. Subset. I wonder when the point will be where I just start writing things in latex on the board. Like, maybe I should put here like, I don't know, subset or something. A to the, like that, maybe that would be better, I don't know. No, maybe. Okay. And similarly, the past attractor, I would denote as A minus, is just given in terms of the alpha. So it's another. So something like this then. So if I drew one more diagram, and I'll be a bit more neater actually with this one. So call this x1, call this x2. So these are just equilibrium points, x3, x4. And let's draw some orbits. So let's go from there. Let me do one that goes from there. Let's go from x4 to x3. Let's go from x1 to x3 as well. And let me have a bunch that are going to x4. So something like this. So the claim is that x1, you can prove, is a past attractor. Why is this? Because all of the solutions are emanating from x1. So you can trace them all back in time to x1, if you see.
So you got a proof negative that is come back to national
Something like this. But the point is x1 is what we call a past attractor, because you can reverse all the orbits and you can see they all start from x1. And you can say similarly that x3 here is being approached from every possible orbit. So it's a possible future attractor for this. So x3 we say is an example of a future attractor. So this is a way of visualizing what it is I'm talking about. And so for the example here, we would say that A plus is x3, and we could say that A minus is x1. So it just says. So x3 attracts future orbits, and x1 attracts all of the past orbits. They all come from x1. Yes?
And is this globally or?
Globally. If you see x1, it has to be global a past attractor, because all of the orbits are starting from x1. Yes, I was just going to write that. Okay, so note that, as you can see from this diagram, A plus does not contain all omega limit sets. You can consider x4 to be a possible omega limit set too, if you just restrict to points on the quarter circle. So that's another way. But in general, this is the way you describe the global behavior of the system. But how do you find these things? I've told you a lot about, but So there's a bunch of theorems that you can find in, for every Russian textbook, there's 3 theorems that nobody's ever heard of before. But they're the most useful theorems in life. I don't know.
You keep bringing up these Russian textbooks. There's translations, right?
For most of them, yes. For a lot of them, you have to find a Russian professor and ask. So I ask Alexei every time I have a question, like, what does this mean? So Alexei Kuznetsov?
Yeah,
Yeah.
Yeah.
he's great.
He's great, and he translates a lot of stuff for me.
Change this title.
After the USSR broke up, like, it was very sad, like, a lot of this material just disappeared. In physics, cosmology, mathematics. You can still find them, but it's very difficult to find because they've also not kept a good way of keeping track of all these applications. But there's no archive you can search online. They're very difficult. Okay, and I will just... So how do you find these things? It's great to draw them out like this, but if I give you a dynamical system, how can you tell me just by looking at it what is going to be the future effective passive effective? And the main theorem here is what we call the form. It's called the LaSalle invariance. So, consider once again my dynamical system. Okay. With my flow phi. Let S be some closed, bounded, invariant set. And let Z be my monotone function that I described. Monotone decreasing function. Then, for all points, which I will call x0, within this invariant set, so within S, we can state the following. The omega limit set, x0, is given by the set of all points in S such that Z prime is equal. That's how you find the omega limit set. If you can find an invariant set, first of all, for your dynamical system, and then you can find an associated monotone decreasing function, and moreover, the derivative of that function in this set is equal to 0, for that point, which the derivative is 0, that is an omega limit. And this tells you how to find the future.
So is that monotone function always going to be in the set S?
No, you have to make sure it is in there. So it's a bit technical, because as I said last time, as there is a lot of questions out there, finding an invariant set of your system, say for that trick I showed you last time, is a difficult thing to do in general. And then making sure your function is also monotone decreasing in that set is a doubly difficult thing. So this is why I said, this is but one theorem. There are others which are extremely complicated. But in general, finding the whole behavior of your system is a very difficult thing to do. Because it relies on you having knowledge of what the invariant sets are, how to find these monotone decreasing functions. It's not an easy thing to do. So this tells you the omega limit set, and this is for the case where S is what we call positively invariant. In other words, we have a positive semi-flow. And the alpha limit set is the same thing, it's just with a negatively invariant set. Okay. And the final thing I will say, then we can start examples on it. Last thing, I know I'm over time, I want to write one last line, because I want to conclude So definition. We say that a finite heteroclinic sequence is a set of equilibrium points. I'll call them E0, E1, all the way to En, let's say, where E0 is a source, En is a local sink, and the rest are settled. So if you have some orbit in your dynamical system where it connects a source to a sink, and in between the source and the sink you have a bunch of saddles, that's called a finite heteroclinic sequence. So I didn't draw one there. But, no. And finally, so what do you do now when you're given a dynamical system? What are the steps then, in summary? So, given x prime of x, what do you do? Right? So step one, try to solve it. But you cannot do it. Obviously, if you can find the solution, then all this stuff doesn't matter, but in general, you can never come to it. So then what you do, you find all of the equilibrium points, which are solutions to f of x is equal to 0. Then you compute the Jacobian ratio, which I've been just calling df of A. Then you study the eigenvalues. And in particular, the signs of the eigenvalues, signs of the real part of the eigenvalues. And then 5, if you're fortunate, you say something about the omega and alpha limit sets using the Lasso invariant. There's one more theorem that I'll talk about in the context of an example, and that's finding number 6 maybe, what we call the Lyapunov function. So LIAPUNOV function. And that is another way of determining global behavior. So, but like I said, 5 and 6 could be impossible to do. Steps 1 through 4 is typically what you do. And finally, number 7, you describe or determine the heteroclinic / homoclinic orbits / sequence. That's it. So that is how dynamical systems work. That is the machinery behind them. And we will apply this now on. Any questions about that?